This is unbelievable. SpaceX's Flight 12 booster 18 is no more. It just exploded. Rocket Lab launches hypersonic test flight.
Hey, I'm Lucas. Welcome to the SpaceX community. Let's get started.
On November 21st, 2025, Super Heavy Booster 18, the first flight qualified version 3 booster for SpaceX's Starship system, suffered a catastrophic structural failure during cryogenic proof testing at the Masseys test site in South Texas. The incident occurred in the early morning hours while the vehicle was undergoing what was believed to be an ambient temperature or low-pressure cryogenic proof cycle using liquid nitrogen. Live streams from LabPadre, NSF, and various ground observers captured the sudden and violent rupture of the oxygen tank section, resulting in the entire LOX tank barrel being peeled open along multiple longitudinal seams. Here, I'll go more in depth into the sequence of events, the visible damage, possible root causes, implications for the V3 program, and the broader context of Starship development. The test began normally, with Booster 18 standing fully stacked on the Masseys orbital test stand. At approximately 0630 local time, a massive white plume erupted from the lower half of the vehicle, initially mistaken by some observers for a routine vent or deluge activation. Within seconds, however, it became clear that the plume was accompanied by structural deformation. Photographs revealed that the liquid oxygen tank had failed catastrophically, with large stainless steel panels folding outward in a characteristic flower petal pattern. The methane tank above the common dome appeared intact, and the forward skirt and thrust section remained upright, but the LOX tank was effectively destroyed along its entire length. Unlike previous explosive failures such as Ship 36 earlier in 2025, no ignition occurred, likely because the test had not yet progressed to methane loading and a propellant in use was inert. Multiple community sources quickly shared detailed imagery that confirmed the extent of the damage. Photographs posted by Starship Gazer showed the booster from multiple angles, clearly illustrating that the failure originated in the lower LOX tank and propagated upward along weld seams and stringer attachments. Additional close-up images revealed exposed downcomer pipes, stringers bent outward, and large sections of the tank wall, completely detached, yet still tethered by remaining structural rings. The vehicle remained remarkably upright on the test stand, a testament to the integrity of the thrust puck and skirt section, but the LOX tank itself was peeled from the middle. Now, Booster 18 would be declared a total loss and scrapped on site, marking the first complete destruction of a flight-ready Super Heavy booster during ground testing. While SpaceX has not yet released an official statement or telemetry data, preliminary analysis from experienced engineers and longtime observers points to several plausible failure modes. The most commonly discussed theory centers on weld quality or material inconsistencies in the new version 3 tank design, which incorporates thinner 3.97mm steel in certain sections and redesigned common domes aimed at mass reduction. Another possibility involves an overpressure event caused by a stuck valve, ground-side procedural error, or an unexpected auto-vent failure that allowed pressure to exceed the tank's proof limit. Some have noted that the rupture pattern resembles classic hoop stress failures seen in early Starship prototypes, such as Mk1 in 2019, suggesting the burst pressure may have been lower than anticipated. Because the test was reportedly still in the ambient or early cryogenic phase, the fact that the vehicle failed well below its intended cryogenic proof pressure of approximately 8.5 bar has raised particular concern about fundamental changes introduced in the V3 architecture. Booster 18 represented a major leap forward for the program. As the first fully V3 configured flight article, it featured stretch tanks providing an additional 250,300 tons of propellant capacity, redesigned Raptor engine mounting, forward-mounted avionics and battery sleds, and numerous mass-saving improvements intended to push payload toward 200 tons to low Earth orbit in expendable configuration. The booster had completed stacking only weeks earlier and was expected to support Flight 12 or Flight 13 in early 2026, following successful proof testing and static fire. Its loss now forces SpaceX to rely on Booster 19, which has yet to begin final stacking, and will almost certainly trigger a stand-down while every weld, material batch, and design change unique to V3 is re-examined. This will delay the operational debut of the stretched V3 vehicles by at least several months, and may push the first Block 3 flight into the second half of 2026. The intact upper methane tank and forward section meant engineers would have unprecedented access to internal components for forensic analysis. The thrust section, engine bay, and the majority of the 33 Raptor engines appeared undamaged, offering potential salvage value. Recovery crews were expected to begin detailed inspections within hours, and the wealth of high-fidelity telemetry from a fully instrumented flight article will provide SpaceX with critical data on exactly where and how the tank failed. Fixes are likely to be relatively straightforward, whether improved welding procedures, additional stringer reinforcement, or minor geometry changes, and can be rolled into Booster 19 and subsequent vehicles with minimal schedule impact once the root cause is confirmed. In the broader context of Starship development, incidents like Booster 18 are painful, but not unprecedented. The program has lost more than a dozen vehicles to explosions or structural failures since 2019, each providing lessons that have steadily improved reliability. Early prototypes routinely failed cryogenic proofs, yet today Block 2 boosters regularly achieve full dutation static fires and flight-proven reuse. The V3 transition represents another major iteration, similar in scope to the move from Block 1 to Block 2, and setbacks of this nature are part of stabilizing a design that ultimately needs to be both higher performing and rapidly reusable. While the loss delays near-term goals such as increased launch cadence and the introduction of in-orbit refueling demonstrations, it also ensures that systemic issues are addressed before the fleet scales to dozens of vehicles. Quick update for you all. If you haven't joined our community yet, we'd love to have you. It's completely free, just hit the subscribe button. A few of our members mentioned yesterday that they're not receiving our daily episodes, and I'm not sure what's going on there. So, if you could do us a favor, like this video and make sure your notifications are turned on. Thank you so much, and now, let's get into our next news. Rocket Lab's latest hypersonic test flight marked another important milestone for the company as it continues to position itself as a key commercial partner for the U.S. defense community. Early yesterday morning, the suborbital HASTE vehicle lifted off from Launch Complex 2 at the Mid-Atlantic Regional Spaceport in Virginia, marking the sixth mission in the program's growing flight history. At liftoff, the mission carried a primary payload developed by Johns Hopkins Applied Physics Laboratory, along with several secondary experimental packages from additional government and industry partners. The details of these payloads remain undisclosed, as is typical for national security testing, but the flight profile was designed to support hypersonic research, including data gathering on high-speed aerodynamics, guidance behavior, thermal performance, and potential missile defense applications. This is the core premise of the HASTE program, to provide government customers with fast, repeatable access to suborbital hypersonic test conditions without the long development timelines and costs that historically constrained hypersonic flight research. Derived from Rocket Lab's Electron architecture, but modified for suborbital operations, HASTE has proven capable of flying high-energy trajectories on relatively short notice. This latest mission took place roughly 14 months after contract signing, highlighting the company's ability to deliver rapid turnaround for defense customers. That responsiveness has become a defining characteristic of Rocket Lab's national security work, especially as the demand for reliable hypersonic test environments increases. Since debuting in 2023, HASTE has now flown 6 missions, marking one of the most consistent modern hypersonic flight test programs in the United States. The increasing cadence demonstrates not only the reliability of the vehicle, but also the growing appetite across government organizations for more frequent and iterative testing. Historically, hypersonic development has suffered from infrequent launches, high costs, and long program gaps that slowed the rate of progress. By using a commercially operated platform like HASTE, agencies can gather data more regularly, validate new materials and guidance concepts, and refine experimental payloads at a pace that aligns more closely with modern development cycles. This latest flight also underscores the strategic importance of Wallops Island and Launch Complex 2 as a location for national security launches. The site provides coastal range access, experienced operations teams, and an increasingly active launch cadence. As the program grows, Wallops is becoming an important hub for responsive, suborbital government missions. For Rocket Lab, operating from this site gives the company flexibility in scheduling, rapid pad turnaround, and a clear path toward expansion as demand increases.
Thanks for watching today's episode. Don't forget to subscribe and give us a thumbs up if you enjoyed it. Stay tuned for another great video tomorrow.